Christian for suffering a little bit in organizing this. It's a pleasure to be in Bonn. I always feel intimidated by the concentration of mathematics, which is here, particularly at the Hausdorff Institute. Okay, so this is a bit strange to the audience here, but I have to say that I promise you mass transportation and stuff related to the classical inequalities. By the end of the talk, I'll start with the classical stuff, and then move very quickly to random matrices, and then see what this becomes in the limit. So my limits are not going to be the classical limits. Like the classical in this audience is basically Gromov-Hausdorff limits. It's going to be something different, and it's driven by the free probability approach and so on. So Nicola is not here, so I'm going to introduce the W2 distance. He was hesitant yesterday to do this, but I have to do it. So if I take a Riemannian manifold, W2 is given by the best, take the best coupling, which best meaning minimizing this distance of xy squared, integrate pi. The marginals of pi are mu and nu. And this is a metric for the weak convergence on probability, on probabilities with finite second moment. And then the Brenier map, there exists a map which takes this form, is the gradient of some convex function. It's the exponential of a minus gradient of f, where f is d squared over 2 concave. And this maps nu into mu, and the best plan here is the push forward of t and identity of this reference measure nu. And then the distance basically is the integral of dx tx squared against the reference measure nu. So that's basically the classical case. I should probably not even put this slide here, okay? But okay, and then I'm going to talk about, the classical inequalities here are just the transportation inequality, log Sobolev, HWI, and one of the weakest of them is the Poincaré inequality. So I say a measure nu satisfies the transportation inequality if I can measure the relative entropy of mu with respect to nu. If I can bound that from below in terms of the Wasserstein distance squared and rho there. So, and then I say the measure nu satisfies the log Sobolev inequality. For any other measure mu, I have this inequality where I is the Fisher information, and then I say satisfies HWI inequality if there is sort of similar to log Sobolev, but on this right-hand side I put something which involves the W2 and the Fisher information, and this is definitely stronger than this. This is due to Otto and Villani and so on. The weakest of all of the family is the Poincaré inequality, which states that if it states that nu satisfies the Poincaré inequality if for any smooth function f, the variance with respect to the base measure nu is bounded by there is a row missing there. Is bounded by the gradient of f squared, d nu. Okay, so I should probably mention that just a few results. Basically, I copied and pasted this from Otto and Villani, saying that if nu is e to minus xc dx, where dx is the standard measure on a Riemannian manifold, and I have the Bakry-Emery condition here for some positive rho, then HWI with rho holds. It doesn't have to be positive. This constant rho doesn't have to be positive. The log Sobolev implies the Talleyrand, where the transportation. Then the other way around is true. The transportation implies log Sobolev with different constants, but I will probably not discuss these in very much detail. The transportation log Sobolev and HWI for rho positive imply the Poincaré inequality. So that's the classical theory. Now I just want to emphasize on the fact that you need the Bakry-Emery condition here in order to get all these nice results. if you don't have the Bakry-Emery condition, then you don't know what to do. Okay, now I'm skipping to random matrices, and this is a slide containing most of the theory, so I have to go slowly on this. So what is the story here? I'm going to take now a large N, and I'm looking at Hermitian matrices, N by N Hermitian matrices. Put there the Lebesgue measure, which is the natural Lebesgue measure you can put on this space. And then I'm taking the probability. So suppose I take a potential Q, basically a function on the real line, and I'm looking at the trace. Q of M is just the functional calculus. This is Hermitian. I can define Q of M. And then I take the trace of that, put minus N in front, and then declare this is basically the density of my, my measure. I have to normalize everything by 1 over Z and Q to make this a probability measure. Because if I don't normalize it, I don't have a probability measure. Now, the first thing I want to see is what happens to the entropy. So if I take two such potentials, Q tilde and Q, and I'm looking at 1 over N squared, the relative entropy of this measure with respect to the other measure. Let's call this base measure, and Q tilde being another reference, another measure. Then if I write what this is basically the integral of the density times the log of the density integrated against P and Q. Well, if you work out this calculation, it's not so complicated to do this, but you'll see the log of Zn, this constant, corresponding to Q tilde, popping up in front, and then the constant corresponding to Q popping up in here. And then we have 1 over N, the trace of Q tilde M minus QM, this integrated against the measure P and Q tilde. Okay? Now, one of the issues here is to understand what happens when N is very large. When N tends to infinity, you would like to understand what the asymptotic of this thing is. The easy part is to understand this from the free probability context. So I'm not going to discuss too much on this, but I mean, one of the issues is here, so in order to compute this, show this converges to something when N tends to infinity, you have to do something, and I'm not going to insist on that. I would like to insist a little bit on what happens when N tends to infinity to this quantity. And the way of doing that is going through passing from the matrix to eigenvalues. So what does it mean? It means that instead of looking at this matrix, I just want to diagonalize the matrix. So basically take the eigenvalues, and M can be written as a conjugation of a diagonal matrix. So the conjugation goes away, and so so if I take a matrix M, I'm looking at the distribution of eigenvalues. I'm calling this measure, which leaves on the real line this time, okay? Because the Hermitian matrices have all the eigenvalues on the real line. This is important in this context because I'm going to move to the complex case, and all the eigenvalues are going to live on the circle. So this is actually a measure on the real line. So Z and Q is basically the integral of this density, and the first thing you can do is just diagonalize M. Basically, you have a transformation, compute the Jacobian and all that nice stuff. I'm lying a little bit here. Z and Q, if I move to the eigenvalues, is going to be given by this integral. So I'm just integrating the eigenvalues. There is another constant here, which I'm going to ignore for the purpose of the presentation. The constant there is going to be the same independent of Q. And therefore, if I take the minus the difference of the logs, that is going to disappear. So I'm not going to insist on that. What I want to show is that it's very natural if you diagonalize M, then Qm, trace of Qm is just the sum of the eigenvalues, right? But there is another term coming from the Jacobian, which is the product xi minus xj squared. And then you integrate this with respect to the eigenvalues. Now, I'm going to arrange this crazy thing into the following. So it's just the exponential of force out n squared, and then I write everything in this form. So this is the sum of qxi. And this becomes log of xi minus xj with 1 over n squared in front. And then I integrate this. I can even write this in a nicer form in terms of this measure. So this is going to be what? Just the integral of q with respect to this measure, qnx dt. And this is going to be a double integral with respect to nu n. And then one of the questions I have to answer here is what happens to this when n tends to infinity, right? And when n tends to infinity, basically I have to look at what happens to this thing when n tends to infinity. And maybe this is a nice point to break it, as an elementary question, if you have the integral of e to minus lambda, let's say just on the real line, dt, and you want to understand the asymptotic of this when lambda is large. Do you know how to do this? It's if, let's assume ft is convex. So let's write ft as being ft0, t0, the min. Yeah, it's called the steepest descent. But basically, if I take t0 to be the minimum point, this is t minus t0, f prime t0, plus t minus t0 squared over 2 f double prime t0. Well, this goes away because t0 is the minimum point, okay? And then this becomes e to minus lambda f t0, okay? And then e to minus lambda t minus t0 squared over 2 f double prime t0 dt. Do we know how to integrate this? Well, in principle, this is a constant, so this is e to minus lambda ft0. And notice ft0 is just the minimum of this function. And the rest is a quadratic function, basically. So t minus t0 squared over 2 dt. Do I know how to compute that? Well, 1 over square root t, right? So approximately what I get here, e minus lambda ft0 times a constant over square root lambda. And of course, if I want, I can get more asymptotic terms. But to exponential, at the exponential level, decay basically of this is controlled by the minimum. So in other words, what it means is when n is very large, I should expect this thing to be controlled by those points which are somehow minimizing this energy. And that's the key transformation of the relative entropy from the classical point of view into the relative entropy of the free probability. So basically, what I'm saying is that if you take this seriously, the steepest descent argument, you can see the exponential decay is driven by the minimum point. So therefore, I should expect that this integral should basically be controlled by those, well, by the function, by a measure mu, which is somehow related to the minimization of this energy, if you want. Which, as a function of mu, yes. So as a function of mu here, this is a linear part, and this is a double integral. And you're right, it's not a trivial question, but it happens to be actually convex. Yeah, it's okay. So what the moral of this is that this quantity here basically becomes, when n is very large, becomes converges to this energy evaluated at some measure mu, q tilde minus this plus, it turns out that this whole term here converges to something like q tilde minus q integrated against the measure mu q tilde. Of course, I can't cover all the details, but this is somehow a crunch of what happens when you pass from the classical inequality, from the relative entropy, the classical relative entropy, you pass to the limit when n tends to infinity, and you get something relatively different. Okay? It's an entire business here. Basically, this one is related to the large deviations of these measures. This is a random measure seen under this probability measure. This is a random measure. There is a theory developed by Alice Guionnet and Gerard Benarous. Okay, and this is responsible for what is called the rate function in that case, and it's related essentially to this calculation. Okay, so that basically boils down. Now, if I want to prove, for example, if I want to apply transportation inequality, let's assume that Q is a convex function, and convexity, strong convexity is given by that. And if I apply the classical transportation inequality on this large space, and then divide everything by n squared, and then let n tend to infinity, this part converges to something like this. This part converges to the Wasserstein distance between, well, at least it's bounded from below, I should say. It doesn't converge exactly to that. It's bounded from below by the Wasserstein distance between mu q tilde and mu q. Okay, and on this side, I will get what is going to be the definition of the relative entropy in the free probability case. So it's, you see, it's sort of a limit, but the dimension goes to infinity in this case. So it's okay. That's what happens in this case. Now, because we saw how this thing appears, now I can actually define this very, very nicely in terms of, let's call this free entropy. Take Q as smooth potential, let's say on a closed subset. I can do this in very, very great generality. Take a closed subset of the complex numbers and impose some condition like at infinity should grow at least logarithmically faster than logarithm, and this is if k is unbounded. If, for example, one of the main cases I'm going to talk about is the k, the real line, and the circle. So in that case, for the circle, I don't have to impose any strange conditions like growth at infinity and so on. And the energy for a measure is yes, x squared here. What do you mean? Yeah, it does. What do you mean? It doesn't seem so. Yes. Well, okay, I see. Okay, you can put log of the absolute value of x. Okay, yeah. Some people actually are very, so let's say if this is greater than 1, strictly greater than 1, that's sufficient to guarantee some results. But in principle, people can consider this case. I mean, I put 1 plus x squared here just to make, you know, not bother with what happens at 0. Some people prefer to say this is greater than or equal to some constant for all x and so on. So, okay. That is necessary, for example, if I go back here, if I want to make sure this is integrable, for instance, I need to impose some condition on the growth of q, because otherwise this is not going to be finite. So that's, for example, just try to make sure I have enough integrability. But so I consider this EQ of mu to be the integral of the potential against the measure mu, and then it's minus the log of x minus y, mu dx, mu dy. So this is, even though this is fancy, it looks like coming up from random matrices and so on. This is actually this is an old object. It was considered initially by Gauss himself, and it's basically related to how charges actually stabilize. If you put, so Gauss considered this energy without this potential here. So he considered the case of an interval. Okay, you put a charge on an interval, and then you want to understand what is the distribution of the charge at the equilibrium. Okay, and that basically, this log term amounts exactly for that sort of interaction between electrons, for instance. You know, they have the same polarity, they repel each other, they are forced to stay on this interval, and Can you guess what the distribution is in that case? So if I take just an interval. Well, of course, because they repel each other, they are forced to stay on an interval. Is going to be more electrons at the ends rather than. So that is going to be the arc-sine law. Has more density. You find more electrons at the end of the interval. However, if you let the electrons stay on the real line, of course, if you don't consider any potential forcing the electrons to stay somewhere compactly, then without any potential, they will basically go to infinity. So you just won't have a solution to that. This is why you put a potential there to make sure the electrons are staying in a certain region. Okay, and this is a well-studied object somehow, and the main result is that there is an equilibrium measure, basically one minimizing this energy. And in fact, there is a unique such equilibrium measure. So, under this condition, even more, mu q has compact support. I think one of the big problems in this case, if you want to determine the measure, is what is the support? So you start with the support, and then you try to analyze, try to understand the measure in terms of the support. Typically, the measure has one cut if you impose some convexity conditions on Q. Otherwise, it can have any support, and then it's very difficult to find it. So typically, you can characterize this variationally. You say that Q is going to be greater than or equal to the logarithmic potential of mu Q. So I should have here dy, not dx, because this is the free variable, and then this is the dummy variable. So this is going to be Q greater than or equal to this, plus a constant. Equality is going to happen on the support. In case the real line, then, and the support is the union of intervals, because if it's, for example, it could be in principle a counter set if I don't have any other constraints. And then I can't say too much about that. But if K is equal to, is the real line and the support is union of nice union of intervals, then I can take the derivative of this equality on the support and get this characterization. If you look at this, this is called Hilbert transform, or principal value integral of mu q. For the circle case, I won't have exactly this, but I'll have the cotangent of x minus y divided by 2 if I interpret the circle as the interval minus pi. Okay. So and then I'm going to call relative free entropy to be defined. If I take the potential q, I define the measure mu q, and then the relative entropy of mu with respect to mu q is just the difference of these two objects. So this is basically the minimizer, and then I subtract from eq mu that. And this is positive, is always positive, is 0 only if and only if mu is equal to mu q. And what is actually encoded here in the positivity, unless mu is equal to mu q, is the uniqueness of the equilibrium measure. Otherwise, you get. Okay, so the famous cases are q equals x squared over 2 on the real line. The minimizer of the free entropy is going to be the semicircular law. And the minimization EQ here is going to be, I'm going to call EQ just the minimizer of this thing, is going to be 3/4. On the circle, if Q is 0, the equilibrium measure is the Haar measure on the circle, as one should expect. Okay. Now, there is a version of the free Fisher information. It's given by that. The interesting aspect of this is that I have to consider here the Hilbert transform. So on the real line is going to be just the Hilbert transform. On the circle is going to be cotangent x minus y d mu. Notice the one very weird thing here is if you consider this as a function of mu, it looks like it's cubic rather than quadratic, as it is in the classical case. But that's what it is, and it comes naturally again if you take the random matrix heuristic or approximation. then the Fisher information becomes this crazy object. Okay. Now, there's certain inequalities in this free case which are due to, the first one is due to Bian and Voiculescu, shortly after Otto and Villani published their paper on transportation, log Sobolev, and implications between these. And so if Q is x squared over 2, then we have a transportation inequality. Basically, the Wasserstein distance between mu and mu q is going to be bounded from above by very, very classical. Then later on, Hiai and Ueda and Pats published a paper, I think it's in PTRF, if I'm not mistaken, improving this one to just, if you have strong convexity, then you have transportation inequalities. And they proved this using random matrices. Hmm? That's right, that's right.
Oh, it's a purpose. You missed that factor too, really?
No, 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 I missed it.
Ah.
I think I missed it, yeah. So, yeah, should be rho over 2 here, right? And then Bian and Speicher actually had another, I think Bian by him, together with Speicher for this case, they proved the log Sobolev inequality, and then later on Bian proved the log Sobolev in this convexity case for using random matrix approximations. Okay. So that's the inequality. Looks very classical. I mean, it's exactly the same as in class. Now I'm going to move to the unitary case. Basically, now I pointed out here that this is the probability measure on the Hermitian matrices. Now you can do the some similar heuristics. Yes. That's basically the idea. Yeah. But the problem. Yeah. The problem is you can't prove the HWI using random matrices. It is known because I proved it with Ledoux, but it's not. You can't get that using random matrix approximation. And I'm going to. Oops. What happens here? What is Alt F for? Again, it means known to be good, but it's not known how to get it using random matrix approximation. There's no statement that it's impossible to get it. That's right. That's right. Okay. You see here the passage from this to this is basically, if you take the lim inf of this is going to be greater than or equal to that. But you can't prove it the other way around. So if you want an HWI inequality, you need W2 on this side. Right? For an HWI inequality, you need W2 on this side. Well, the best you can hope is that is to bound lim inf or lim sup of this by this from below. But it's not. There is no way to bound it from above. So at least this is why some of the random matrix arguments don't work in this case. Okay, that's one of the issues here. But yeah, okay. So now, if I move to the unitary case, then I can take the Haar measure on the n by n unitary matrices. I take very similar to the picture before, minus n trace of q of m, where I force this q to be a potential taking real values such that this is well defined, so this is a probability measure and so on. H is the Haar measure on the unitary group, and then I'm trying to apply the same arguments as before. The problem here is that the Ricci on the n by n unitary matrices is almost constant, except one dimension in which the Ricci degenerates to 0. And then what do you do there? So I think Hiai and Pats did the following. So basically, because the Ricci is 0 in one direction, you can't apply the Bakry-Emery condition. You can't use the Bakry-Emery condition and so on. What you can do is basically reduce the group. Instead of taking all the unitary matrices, you take the matrices of determinant 1, then Ricci is n times n minus 1 over 2. So that's okay there. and then you can run the argument with the smaller subgroup, and then what you get is if you have enough convexity, basically Q double prime plus 1/2 is greater than or equal to rho. That guarantees the Bakry-Emery condition on this group Gn, and then you can run the random matrix approximation. What they get is an inequality in which you have the W2 here and the relative entropy on this side. So everything looks classical. And then they also get the log-Sobolev inequality, which now is the relative entropy is on this side. On this side is the Fisher information minus a correction. So this is basically what happens in this case. So at first reading, I was just saying, well, okay, they got another term there. It's not a big issue. Notice one thing. If Q is 0, basically I'm looking at the Haar measure on the unitary group. Then Q is 0 here. And then mu, the equilibrium measure associated, is just the Haar measure on the circle. Well, if you have the Haar measure on the circle, what is this? If you integrate the derivative of a function on a circle with respect to the invariant measure, that's going to be 0. Okay, so if Q is 0, oh well, if Q is 0, that is going to be 0. So it's not a very clever remark, but okay. So at first reading, I just discarded that thing. But and then I said, well, maybe one can actually also prove some Poincaré inequality from the random matrix approximation. So how does it work? It would work like this. I take a function on this unitary group of the form trace of another function of the matrix. And I apply Poincaré inequality, okay? And then pass to the limit. When I pass to the limit, something interesting goes on. Namely, this variance term goes to something like this. Alpha here is going to denote the Haar measure on the circle. And this term goes to this term. Okay? Now this is more interesting to some extent. Why? Because now if Q is 0, then I have the integral of f prime d alpha. Okay? If alpha is the Haar measure on the circle, this is going to be 0. Okay? So there is nothing very interesting here. I should also make this remark that even though the measure appears on this side, it doesn't appear on that side. The measure mu q. This is a new phenomenon in this free Poincaré context, which is due to the fact that you have what is called in random matrices some sort of universality. No matter what your potential is, the variance of this thing is going to converge to something which is independent of the potential you started with. So therefore, the Poincaré inequality is going to take a different form. You have the measure mu q on this side, but you don't have the measure on the other side. Okay. There is also something here, namely, I can't apply really Poincaré inequality on the whole group UN. I have to, again, because I don't have Bakry-Emery conditions, so I can't run the arguments, the usual arguments. I really have to restrict myself to the group of matrices of determinant 1. So this gradient here is going to be the gradient of f restricted to the subgroup G of matrices of determinant 1. And what does it mean? Well, how do I compute that? So basically, I have here is the whole group UN. I have a subgroup inside G. Okay. At each point, I will have at each point in G, I will have the tangent. This is T of G for a matrix. But I also have the other direction in which the Ricci on UN is degenerate. Okay. How do I construct that? This vector basically is the derivative. This vector here, V is basically the derivative with respect to t, 1t is equal to 0, e to power I t times A. All right? So if A has determinant 1, this matrix doesn't have determinant 1, has determinant given by this e to power I n I t. So this is basically this direction in which the Ricci degenerates. And then the gradient of f on this group G is going to be the gradient of f on the whole un minus the gradients, or minus f prime v, okay, squared. Well, this is, I have to put squares here. This is what one should expect. This actually is going to converge. F prime is going to converge to that thing, at least from this point of view. If I integrate this against the measure, this is converging to the integral of f prime d mu q f prime squared. But this term, if I look at this term, this is basically the integral. I can write it as trace f prime m, okay, and square this, integrate. It turns out this thing is converging to f prime d mu q squared. Okay, so this is how this factor comes out by just observing that the directions in the tangent space in un basically splits into two parts. One is the tangent to the group G, and the other one is the isolated direction. So when you consider the gradient there, the gradient of trace of Fm, you basically get the component which is coming from the whole group minus some correction. That correction converges to that. Well, so this is the free Poincaré on the circle. We can now have a definition of a Poincaré inequality on the circle, free Poincaré. Yes. Indeed. It's exact. Yeah, you get this Poincaré inequality. Yeah, it's consistent. Well, there is a little bit of proof here. I mean, this is okay, but if you want to prove the transportation implies the Poincaré, then you have a problem. Well, it's more or less, but the problem here is basically how do you compute this thing when you basically you're saying, well, let me perturb mu q by a little bit. What do you mean by a little bit? How do you perturb mu q? Because this is how you get the Poincaré from Loxobol. That's right. That's right. Yes, but I'm saying you perturb this measure. You replace mu by 1 plus f times mu q. Okay. Well, that doesn't seem to be working very nicely in this case. But if you perturb, if you take mu to be mu q plus tf, okay, where t is small, then you get exactly the Poincaré inequality. This is sort of I'll point out a certain place in this talk what the issue is. The issue is you really have to consider what happens to this when you basically perturb let me see. Okay, we can discuss this after all, because I'm used to perturbing it like that, and then you get this Poincaré inequality, okay? Sort of linearization. But if you don't perturb it like that, you get eventually something different, okay? So, yeah. Okay, so the Poincaré, the free Poincaré on the circle is that for a measure on the circle, basically you say satisfies the free Poincaré inequality with some constant. If you have this on this side and this quantity on the other side, so basically you are measuring something depending on mu with something which is independent of mu. So it has a very different flavor from the classical Poincaré inequality in the sense that this side doesn't depend on mu. What do you mean infimum over all mu's?
You said universality, or maybe I misunderstood. You said that any kind of potential, any measure on Hermitian matrices,
Yes.
under some convexity assumption on the potential Q,
Yes.
will give you a Poincaré inequality.
Yes.
So take take the worst, the smallest
Yes.
right-hand side that you can.
Right, but you still have to preserve. Mu Q comes from the minimization of the energy of some potential. You have that. You have to impose that that potential is going to be convex, strictly convex.
There's a meaning to minimizing this under this constraint.
I don't know. I don't think it's very easy to get that. I don't know. I never thought about that. But, so you want to minimize overall convex functions Q? Yeah. Well, I interpret this being part of this universality of random matrices, which is okay. So, and then, if I take Q to be 0, then this side, for example, is interpreted as being sort of an operator applied to F. So it's sort of a, Dirichlet form, if you want. And then this side here is also a Dirichlet form for another operator. So if I take mu to be alpha, which comes from the case when Q is 0, and then this side here can be interpreted in terms of this counting number operator. So basically, I define this operator N. I define its inverse E. And it turns out that N is basically the counting number operator for Z to power, for monomials, essentially. And then if I take N squared, this is going to be just minus F double prime, which is essentially the Laplacian on the circle. And then this side becomes NF with F, the inner product, with respect to the base measure, the Haar measure. And this side becomes LFF. Because the spectrum is just 0, 1, 2, and so on, it's basically trivialized in this case. So that's the spirit. And somehow, in order to, I had a paper with Ledoux on discussing this case for the measures on the line, and proving that, for example, log Sobolev or transportation implies this inequality. It takes a while to do that. It's not entirely trivial, like in the classical case, because the entropy is not so nice as in the classical case. It's very intricate. I mean, you have to minimize something, and then you take perturbation of that is nonlinear, and so on. So, okay. There are various properties. For example, if you have the Poincaré inequality, the support of this measure has got to be the full circle. I mean, you can have gaps there. And then if you have, this measure mu has a density with respect to the Haar measure, then the density has to be positive everywhere. So, and then a result in this direction is that if Q double prime is greater than or equal to rho minus 1/2, then I have this Poincaré inequality. I should mention that so far you may ask, well, what is new here? Because I can use universality for fluctuations of random matrices. Well, I said that just as a heuristic. It's not going to work for any potential Q which is convex and so on. The proof using random matrices could be tedious. You have to justify this and that and so on. This is a very simple statement, and there is a proof in terms of these operators as in here. Of course, you don't have this nice interpretation of the right-hand side. The left-hand side doesn't change, so therefore it seems natural to interpret this whole inequality in terms of the operator N. Here's somehow a crunch of a proof. it's based on the fact this side is basically n phi with phi. And then there is a strange identity relating n phi phi with the operator E, and then write this inner product, and then do some manipulations because E has spectrum 1 over 2, and so on. This is bounded from above by this quantity, and then you get you force in some operation, some 1 over n q here, and then change this to mu q, and then finally use convexity and get done. So I'm not going to insist on the proof here. There is some refinement. I can skip that. So there is an interesting phenomena. So basically, I want to interpret this correction as being some correction to the fact that mu is not the Haar measure. Notice that if mu is the Haar measure here, this whole term disappears because the integral of f prime on the circle is always 0. Okay? Well, I interpret this term as being sort of a defect, you know, or measuring how far the measure is from a Haar measure. Okay? And I wanted to prove, for example, a transportation inequality using just the hands-on, using transportation method tools. For a long time, I was trying to do this. And one thing I should probably mention is that the result of Hiawe-Dunpetz is the free entropy here is bounded from below by the Wasserstein distance. And this is the typical Wasserstein distance. There is, though, a correction in the log-Sobolev case when you have this q prime. So therefore, I was expecting when I realized what the free Poincaré inequality is, there is a correction here. So this correction, which is due to the fact mu q is not the Haar measure, or at least I interpret it that way, this correction appears in the log-Sobolev inequality. But there is no correction coming up in this inequality. So for a long time, I was trying to prove this one using very simple methods of mass transportation, and I wasn't able to. And then later on, I was able to fix that by changing the Wasserstein distance. The Wasserstein distance basically is the one which works, at least in my arguments, is the following. So I take a measure mu on the circle, and I lift it to the real line by simply, you know, using, it's not a push forward. It's basically, this is no longer a probability measure. It's a measure on the real line. I can actually take, so I can take, you can interpret this as the following. So mu bar u is basically the following. If I take point u here, and u plus 2 pi, okay? This is mapped into the circle, and I can push, you know, this measure on this interval. And then the Wasserstein distance is basically the distance constructed in terms of the distance on the real line between lifts of measures mu and nu, such that they have the same mean on the real line. Okay, so basically I lift mu on some interval, I lift mu on some other interval such that their means are going to be equal. And then I define the Wasserstein distance as being the sup over all possible choices of u and v with this property. And this is the standard Wasserstein distance on the real line. Well, with this, there's some strange properties of this measure, this distance, like the Wasserstein distance on the circle is always less than or equal to this script W2, okay? If you take 2 point masses, the distance between these two is plus infinity unless A is equal to B. If you take the Haar measure and delta A, this is finite. So therefore, if I consider this on a set of all measures, this is not going to be a distance because this is violated, I mean the triangle inequality. But if I restrict this to absolutely continuous or even less masses, measures without any point masses, without any discrete part, then I can actually put always both measures on the same intervals with the same mean. And if I restrict all the measures to absolutely continuous measures, this is indeed a probability, a distance. And this induces the weak topology on probability measures in this space. And there is also a dual formulation of W script squared, which is basically like in the classical case. It's only that I have to add this condition. So I have to lift them on the real line, put them on intervals such that the means are going to be equal. And so the condition is fx plus gy is less than or equal to x minus y squared plus lambda x minus y. And I take the sup over all uv lambda f and g. So this seems to work. At least I can prove the transportation inequality. Yes? Which one? This one? Yeah. Sure. So there's something oh. Yes? Wait. If I take discrete measures, if I take delta A and delta B, I may not be able to find these. So this is going to be plus infinity in that case. There is some discontinuity anyway. Yes? Because, I mean, on those absolute continuous, you can use it about the weak conversion. Yes? You have the triangle inequality, but then you don't have the triangle inequality when you have something non-absolutely continuous. That's bizarre. Why don't you say, I mean, one could say, I think the lower continuous relaxation of this guy. I mean, if mu n converges to mu, and all of them are inside this, yeah, then I have the triangle inequality. Mm-hmm. Yeah, I don't know the answer. Okay. Hmm? Yes, that's right. Yeah, so it could. Yes. Well, yeah, but it's not very clear. If I take delta A and another measure, mu, it's not very clear what happens if I, it's not very clear whether I can put them. I mean, it's not very clear that delta A, if I take delta A and another mu, that is going to be finite all the time.
What's the limit of a delta measure? What's the limit of delta?
It's a delta pointed, you know, it's a sum of deltas pointed at yes, it's not a probability measure anymore. It's basically, so it's, okay, maybe we can discuss that after, okay? So I have a transportation inequality here. If Q double prime is greater than or equal, basically the Bakry-Emery condition, then I have this inequality. The strange thing is that this is definitely not sharp. So if Q is 0, this is going to be the Haar measure. This is not sharp. I conjecture the right if Q is 0, this is going to be rho is 1/2. So I'll have here the inequality with 1/4 in front. My guess is that the right constant is 1/2 there. And I even proved that 1/4 is not sharp. So it's definitely not the right inequality. But I don't know. So the key of the proof is basically everything boils down to proving this. I take theta to be the transport map of mu q of alpha u into, for example, in the case Q0, I take the transport map which maps alpha into mu, lifted appropriately, and so on. And then what I have to prove is this. And because this integral here is going to be 0, because this is how I define this W2 script, then this square here can be written as 1/2 of the differences. And then basically everything follows once I use some convexity. So I'm not going to, I think my time is running up. So I don't know how to prove this. I mean, everything boils down to just because this is equal to that, I can actually prove this inequality is going to be just a convexity argument. But if not, I don't know how to prove it. So I tried using some other, I mean, random matrix approximation eventually works, but I'm not very satisfied with that. I just want one in which I can eventually control the constants and so on. I can do that on the real line, but I cannot do this on a circle. So, okay, so using the same W2, I can prove an HWI inequality with script 2 here, and also the fact that the transportation inequality implies the Poincaré inequality. So this is using the dual formulation. I'm not going through all the proofs here. I'm just trying to say that script W2 is the soup over all lambdas in FGs with this property, and I can use the minimum, the infimum convolution semigroups techniques and so on. So basically replace, like Emmanuel pointed out, basically replace T by TG, basically linearize this whole thing. In the end, I get something which is looking like that. True for any lambda. If I minimize over lambda, I get this Poincaré inequality. So I probably want to finish by saying that now, given this sort of correction, basically all the Poincaré inequality and the transportation inequality now take into account some sort of corrections which are due to not being rotationally invariant. So I was trying to think that there is a classical aspect to this. Maybe this is a, I don't know, problem. So if I take a Riemannian manifold and a Lie group, which is acting isometrically on that, if I take a measure of this form with Bakry-Emery condition, maybe the Poincaré inequality can be improved by sticking in here sort of a gradient, classical, the natural gradient here. There is a row missing in here, of course. Minus sort of a correction due to the fact that mu is not, if mu is invariant under this action, then this thing here becomes 0. And if it's not, then it's something consistent. So an interesting challenge is to see whether a similar modification to the transportation works in this case. So basically, stop here.
Any questions?
Yes. Yes, for the real line case, yes. Yes, exactly. All the constants are sharp in that case. This is some work I did with Ledoux. We get, not only in that case, but also in the case of potentials on half line. So for Poincaré inequality, we can get sharp constants, but for Log-Sobolev and transportation, we don't know. But for the circle case, no, it's not sharp. So